Hello again. Up until now, we've been performing supervised learning. There were labels we wish to predict correctly or a value we wish to approximate closely with a function. Now we look at an entirely different topic, which will be the focus of both this section and the next. Unsupervised learning, starting with clustering. This section starts with a brief discussion about the difference between supervised and unsupervised learning, and specifically what clustering is. Next, we look at our first clustering algorithm, the k-means algorithm, a popular and simple algorithm. Before seeing other algorithms, I discuss approaches to evaluating a clustering scheme. Then I move on to the next two approaches for clustering, the first being hierarchical clustering. The final clustering approach I discuss is spectral clustering. Let's get started. In this video, I will contrast unsupervised learning with supervised learning, the latter of which we have been doing up to this point. I then discuss what clustering is. Supervised and unsupervised learning are two different learning paradigms. So far in this course, we have been performing supervised learning of some kind. There was a variable that we called the target variable that we wanted to predict. This was the case both for classification and regression. Learning consisted of finding a classifier that could accurately predict the target variable. With unsupervised learning, there is no target variable. We believe there are hidden features that differentiate the data, but we don't observe them. The objective of unsupervised learning is to find these hidden features, which we never observe directly, and to assign values for these hidden features to our data and hopefully future data as well. Clustering is the unsupervised learning analog to classification. We start with unlabeled data. We want to group the data into different clusters. We claim that data in a given cluster share a common feature, even though we may not be able to describe what this feature is. There could be many different clustering schemes. While we think similar data points should be in the same cluster, there are many ways to define similarity. Of course, another issue is how many clusters we want. Trivial clusterings include one giant cluster or each data point having its own unique cluster, neither of which are useful. So how many clusters should there be? There is no easy answer, though there are techniques for judging the quality of a clustering. What does it mean for 2 points to be similar? This will be addressed in a later video. Consider first a similar question. What does it mean for 2 points to be different? This could mean the same thing as the 2 points are far away or distant. You are almost certainly familiar with the Euclidean notion of distance as the length of a straight line connecting 2 points on a flat surface. This is not the only notion of distance, though. Others are popular. There's the Manhattan distance, or the taxicab metric, which is the distance to travel to a point when you cannot travel diagonally. There is the angular distance, which is the angle between vectors pointing to 2 points. If we're talking about sequences like strings, we might use the Hamming distance, which is the number of symbols in the string that need to be changed to make the strings the same. Or there's the Jacquard distance, which is the number of elements two collections, otherwise known as sets, don't have in common, divided by the total number of objects in the two collections combined. Choosing a notion of distance is important for clustering. Also, once we accept there are different ideas for what it means to be distant, we can answer different problems more effectively. To drive home the idea of different distance metrics, I want to demonstrate how to compute different distances, all of the ones that I described in the previous video. The first thing I will show is how to compute Euclidean distance, which it corresponds to how we normally think about distance. So I have a function here that computes the Euclidean distance for two numpy vectors, presumably of the same length. So I've created two vectors here, vec1 and vec2, and you can imagine these as lying in a three-dimensional space. How far away are these points from one another? Well, this Euclidean distance function will compute that. They're about 4.24 units away. The Manhattan distance, however, views distance differently. This is the distance between 2 points when you can only travel horizontally or vertically. You're not allowed to travel diagonally. In this case, the Manhattan distance between these 2 points is 6. How about angular distance? The angular distance is defined this way. If you have two vectors pointing to your different points, what is the angle between the 2 points? Whatever angle that is, that would be the angular distance. Now, I would like to point out that there are certain rules that a function must satisfy in order to be considered a distance. We're going to see that for vec1 and vec2, we have an angular distance which is this, and the angular distance between vec1 and vec1, in other words, the angular distance for the same vector, is 0. And any distance must satisfy this property. The distance between a point and itself is 0. But we also have the characteristic that the angular distance between a point and 2 times that vector is also 0. And that would make angular distance not a distance in the mathematical notion of what a distance must satisfy. The distance between 2 points is 0 if and only if the 2 points are the same. If we can find 2 points where they're not the same but the distance between them is 0, then that makes this not a distance according to mathematicians. And yet, at the same time, if these points were to lie along a unit circle, so a circle of radius 1, if those are the only points we consider, then we could consider this a distance along the unit circle. And this acts a lot like a distance, even though it doesn't have that property that mathematicians would like. Hamming distance. If you have 2 strings, the Hamming distance is the number of characters you need to change to make one string the same as the other. Now, I grabbed this code from Wikipedia, shamefully, just because I really liked it. So we have the Hamming distance function, and I have one string 11101 and 11011, and we would have to change this 1 and this 0 in order to make these 2 strings the same. So the Hamming distance between these 2 strings should be 2, which is in fact what this function reports. Now the Jacquard distance. This is defined for collections or sets. It is the number of objects the 2 sets do not have in common divided by the total number of objects in the union of the sets. So I have 2 collections here, cow, pig, horse, and cow, donkey, chicken. So there are 5 unique objects when you combine these 2 sets together, and both of these sets have cow in common, but otherwise there are 4 elements that differentiate the sets. So the Jacquard distance between these 2 sets should be about 4/5, which is what we find. 4/5 is 0.8. Now remember that we're talking about sets. Sets have exactly 1 copy of each element. So this string and this string both have 0 and 1, so when we convert them into sets, they will be identical sets, which means that the Jacquard distance between these 2 points is 0.